This video is about Hooke's law, and it applies to things that can be stretched and then returned to their original position. So take, for instance, this rubber band. It's got two little lines on it and a very old ruler to measure. And when I stretch it, it goes right back to its original position. And just to emphasize that, I've let it go right when it's gone back to its original position. This is said to be behaving elastically, or it's an elastic thing, so that it goes back to its original position. In contrast, we've got things that don't go back to their original position if they're stretched, like this stuff. And if you watch the video, it's got a bunch of silly putty in it, and I pick it up, take it out, and it behaves plastically. It is plastic. And that's because it doesn't go back to its original shape. You can stretch, stretch, stretch all you like. It won't go back to its original shape. Let's say you've got a wire of length L and you extend it a length X. So now you've got a wire of length L plus X. Then what we've got is the force is proportional to the extension. And all that means in math is that you've got F is proportional to delta X, delta meaning the change in X, so it could be just X. And we don't like proportionalities, so we can stick a constant in there. So you've got F equals Kx. And this K is called the spring constant. Now, let's say you've got a spring. So a spring is drawn a lot like that, and it's got a mass at the end of it. And that mass is sitting there under the gravitational force written by mg, which you guys are all familiar with. So let's say that under mg, or under that force, the spring extends to there. And then your delta X becomes the center of gravity there to the center of gravity there. So that's X. Well, we know that there's a linear relationship between F and X. So if F doubles, then X doubles as well. So anything that you do to F, you're going to have to do to X as well, just because of the relationship you've got involving K. So you can actually get a value for M by using this, what they call it, a spring balance. And the spring balance is just another way to measure a mass, just like any other balance. And the other thing we can note about this is that K becomes a property of the spring. So it's just another way to describe the spring. It has nothing to do with the M. It has everything to do with just what the spring is made of. And we'll go into that in a bit more detail in a minute. So as physicists, we love a good graph, so we can graph the F by X, which is just what you've seen at GCSE, and you end up getting a proportional line. In fact, it's directly proportional. And during this directly proportional area, it's got a gradient of K. Now, if you keep applying a force, you're going to end up surpassing this limit, and it'll start to bend. And I'm sure you all remember that this area is the area that Hooke's law is obeyed. This is your elastic limit just there. And then this region over here, your wire or material undergoes plastic deformation. So what's the big deal about this elastic limit? It's because where Hooke's law applies in this region here, you get the bonds in between the atoms of your material stretching and then coming back. They've got a little bit of give in them. But in here, the bonds are either broken or they're residing in a different spot in your material, and so it doesn't return back into the elastic limit. Your material has undergone deformation and it's now plastic. The other interesting thing about this is that you can also compress. So rather than stretch, you can compress, and the same Hooke's law region will apply, and then you'll undergo some sort of deformation, some sort of limit where your material won't return back to base. Okay, so if K gives you the gradient, because F equals Kx, if you get K is F over X, you get your rise over your run, and you've got yourself a nice little gradient. We can also use the area under the curve, which is here, under the Hooke's law region, to figure out the work done in extending your material. So what's work? We've got work equals F times D as normal. And now I'd like you to think about two things. The first thing is that your F is going to be your average F from 0 to the top of your elastic limit. So if you're going to average 0 to F, your average is going to be F over 2. And the other thing is that you've got, under Hooke's law, there's region where Hooke's law applies, you've got F equals Kx. So you've got a little bit of X here, and you've got a little bit of X, it's a D written there, but it's really X there. So with all the force that's going up, your X is going up as well. So with Hooke's law, you've got your work is going to be equal F over 2 times X, which can also be written as Kx squared over 2. So this is also the potential energy when your material is expanded. And when it's expanded and then you let go, it's going to release that potential energy. So this works both ways, as potential and kinetic, which is really nifty.